Okay, guys, let's continue with section 10.6. Continue. Okay, so last time we did the parameterized surfaces. Right? So today we're gonna compute surface area. Two area of surfaces. Okay, so let's sketch our surface here. And I'm gonna look at how we compute the area. So let's say that we have a surface right here. Not necessarily fx squared, or just surface. Okay, down here we get a region D. Something like this is the region D. Okay, so it will take a look at a sample area, and you will see that well, it would be somewhere right here. Right? Put this in here. Sample area. You plot up then in this section right here, 15.9. Remember this? It's this one. So you use the same trick here. Yeah. Use the tangent vector. So one of them is going to be a or U, and then another one is going to be a or V. Well, we want to make the tangent vector the smaller the better. So we use du or U and dv or V. The cross product of two tangent vector, the area of a parallelogram formed by two tangent vector. Okay, here we want the area, a sample area. You want it to be as small as possible. So I'm going to multiply this to a du, and here come dv. Yeah. So that's it. So from here we see that sample area is the magnitude of du or U cross dv of v. Right. So what do we have here? We have the magnitude of RU cross RV and du dv. The area is going to be the summing over the region D of a sample area, and that sample area is RU cross RV dA. Du dv is the same as dA. Where hopefully you still remember RU. So RU is the vector. Partial x with respect to u, partial y with respect to u, partial z with respect to u. RV is the vector. Partial x with respect to v, partial y with respect to v, partial z with respect to v. Okay, special case. Well, the special case is the S can be parameterized by x equal x, y equal y, z equal f, x, y, right? This is the surface in rectangular coordinate. We all know this thing here. If you can do this, that means you can actually simplify the area formula to make your life easy. Still a double integral over the region D. And then this one is all x, because you do x, y, cross all y. dA. So you just have to do the Rx cross RY. I'm going to do the Rx cross RY right here. So if you do Rx, look at this thing here. Partial derivative with respect to x. 1. With respect to x, 0. With respect to x, fx. Oh, how nice. Or y. With respect to y, we don't have any y in the first one, so it's going to be 0. With respect to y is 1. With respect to y, fy. And next, you do the cross product and you take the magnitude of the cross product. Okay, so R x cross RY. Okay. Well, Rx cross RY is the ijk, right? 1, 0, fx. Most of you don't have to write this out, because if you write R sub x next to R sub y, then you should be able to do the cross product right away. 0, 1, fy. I'm just going to write this out for the sake of mathematics. Okay, you look at the first one, right? It's going to be a minus fx, right? And then the second one, it would be minus fy. And then the last one, it would just be 1. Okay, we're almost done here. Rx cross RY, take the magnitude. And that should be a root of fx squared minus plus fy squared plus 1. Is equal to double integral over the region D of this one. root of fx squared plus fy squared plus 1 dA. Very useful formula. Remember last time we parameterized this, and now we want to figure out the area of this one. So I'm gonna just do copy and paste here and save my life. Phi is area. We did this thing last time. I say, look at the surface there. Huh? Surface. Yeah. And we want to find the area of this surface. So, the parameterization we did last time. So there's no need to reparameterize this thing. And do the area now. Area. If you look up here, this is the special case. So the area is double integral over the region D. Root of fx squared plus fy squared plus 1 dA. Man, if you look at fx there, look at this thing here. Double integral over the region D square root fx, that is 1. Fy is 0. Root 2. Double integral over D, 1 dA. What is this? It is just the area of region D. Well, if you look at the region D here, it's the circle of radius 1. So the area of circle of radius 1 is the, a disk of radius 1 is root 2 pi 1 square, or area of this of radius 1. So root 2 pi. Yeah. If you parameterize it this way, then you can also figure out the area. The area has to be root 2 pi, exactly like what we did up there. So area, right? Double integral over the region D. In this case, or cross or theta. dA. So I'm going to do the substitution in here. I'm just going to work out the R. Okay. Partial derivative with respect to the radius R. Cosine theta. Sine theta. Cosine theta. Okay. Partial derivative with respect to the angle theta. Negative R sine theta or cosine theta. Negative R sine theta. And then you got to do the cross product or cross or theta. Okay, so the cross product, right? You can see the IJK here. You can put the IJK here. So I'm gonna help myself out here. Okay, so that would be just be careful when you do this. So it's going to be a negative r sine square minus r cosine square. Okay, that's the first one. And then for the second one, it's going to be a, oh, how nice. Look at this thing here, negative r sine, negative plus, and then that's going to be 0. Right? And for the last one is the r cosine square plus r sine square. Simplify this sucker here. Oh, actually, you can do much though. But then yeah, you can factor the r here and then simplify this thing here. So negative r, 0 r. Yeah. Okay. Once we simplify this, take the magnitude. And that will be root of r square plus 0 square plus r square. So it would be root of 2r square. So it's going to be r root 2. Actually, I can say root 2r here because usually I put a number in front of the variable. Okay, so root 2r, that's what we have. And then now we're going to do the substitution. Root 2, 2 pi times 1 over 2. And you say that, yeah, we got the same answer. Root 2 pi. Find area of sphere of radius rho. Parameterized. S, that is the surface. X equal to, Y is equal to, Z is equal to. Okay. You can look at spherical coordinate, then you will see that X is gonna be rho psi phi cosine theta. We'll just have you up here, rho psi phi sine theta, and then rho cosine phi. Remember this spherical coordinate. So now you just have to know where does where phi the angle theta. Well, if you remember phi, right? This is the sphere, so phi can only go from the z-axis, then you go maximum is up to pi, and then the angle theta is on the xy plane. So the angle theta is, you got to go through the full cycle, 2 pi. From here, the vector that parameterizes the sphere S is, or theta phi, or you can derive phi theta up to you. But I usually do a phi theta here. And it would be first one, rho psi phi cosine theta, rho psi phi sine theta, rho cosine phi. Yeah, what is it equal to? This is, I'm gonna put a note here, no? Note. We will use this in the next section of phi cross all theta is equal to rho square psi phi in future section. Double integral over the region D of phi cross all theta dA. Remember, you don't turn the dA into the spherical coordinate, right? Because we already parameterize the surface is already in spherical coordinate, right? So the dA here, it would just be d phi d theta or d theta d phi, depending on how you set this thing up. Well, if you do this 0 to 2 pi, 0 to pi sub this one, it would be rho square psi phi, and then dA is going to be a d phi d theta. So rho square is just a constant, right? So rho square 0 to 2 pi d theta, 0 to pi psi phi d phi, rho square times 2 pi and integral of sine negative cosine rho square 2 pi and negative of cosine pi negative 1. Okay, actually we have minus cosine 0, right? So I have a 2 pi rho square minus 1 plus 1. So that we are 4 pi rho square. Oh, finally we figure out the area of a sphere, the surface area of a sphere. Pretty cool, huh?